So good afternoon, everybody, and welcome to our new online technology meeting. In this case, we are going to talk about photonics for vision and eye research. And the motivation of this meeting is that we are doing a lot of things related with bio and also medical, both devices and applications. And we found that the ophthalmology and vision research is quite specific in terms of the tools that you're using, the components that have been developed, and also the solutions. And I think it makes sense to dedicate one specific online technology meeting to talk about the latest research in vision and biophotonics related with the eye research, and then to know what is happening in terms of developments from the industry. So that's the main motivation for the meeting today, and we have a great set of speakers. And just to start about EPIC, what is EPIC for those to those of you who doesn't know? EPIC is the European Photonics Industry Association. So you see all the logos in the screen. This is EPIC, is the association of more than 800 companies that are related with photonics. The idea is to create a consortium that can ensure the sustainability of the photonics business by finding collaborations within the consortium, but also finding partners and customers and supplies outside the consortium, and also trying to get information of what's happening outside Europe to establish the best relationship for our members. From the EPIC staff, we are a group of people that are in charge of different activities, and we help of our members with their needs in terms of the technology, in case of they have any request regarding a new supplier, alternative source of certain components, also any request to develop solutions. We also have to learn about markets through our market reports and the mentors to access to new markets. We help with other activities like the human resources support. We have groups to share experiences and also create work groups to help small companies to develop some standards and procedures. We also help companies with investments in both ways, putting spin-offs and startups in contact with investors, but also the other way around, understanding which big companies and venture capitals are interested in investing in photonics. And then I left the networking at the end because it's one of the reasons of these kind of meetings is to bring this whole supply chain about certain topic to the same room, can be online and on site, to discuss about the technology and also to find, again, new collaborations and partnerships. Regarding these networking activities, I encourage you to go to our website to see what's happening next. We will continue in June with our events. This very same week, we have a meeting in Berlin about photo packaging, and we will continue next week with the last meeting before summer holidays about the specialty optical fibers in Lannion in France, where there is a hub of really big expertise of optical fibers. So if you are interested in this topic, you can go to our website and find what's happening in the agenda in the registrations. And we will come back in September. We have EPIC members delegation to Taiwan. This is one of the activities that we do to expand the business of our members outside Europe. So we will travel to Taiwan. This is only available for EPIC members, so you can find more information in our website and talk with Carlos about your interests in this delegation trip. We will continue with two technological meetings, one about photonics for new space and another one for miniaturized optics. We will have also another technology meeting in laser microprocessing in Vilnius, and we will presence in ECOC in Frankfurt. So feel free to join our activities there, or also pass by our booth if you are attending also the exhibition. And regarding online meetings, as I mentioned, we will have the human resources work group, also the sustainability work group, to share experience, as I mentioned, between members and learn from each other's marketing meetings as well, and market reports on perovskite, and then the open online technology meeting that we will have in July about photonics for sea exploration and oceanography. And EPIC, we are also involved in European Union projects about very different topics. So these are the ones that are running nowadays. And perhaps thinking in the topic that we will touch, I would like to highlight MedFab, that is a pilot line dedicated to help companies that are interested in design and manufacturing of medical devices for using photonic technologies. So all the partners there can help a company without the expertise or the capability of using photonics technologies to develop their device. Now they are in the process of moving from a European project to an association. So you can visit the website to see if any of the services that they offer can be interesting for your company in order to help you in your development or evaluation of new technologies that perhaps you don't have the capability to try. And starting with the meeting, this is the picture that we do with all the people registered to this meeting. So it's very interesting, the big amount of companies that we have interested in this topic. Of course, components and modules, because they are very important for a lot of the technologies using in ophthalmology and vision and eye research. So for OCT, light sources, detectors, optical components as well. It's good to have equipment manufacturers, of course, and it's very nice that a lot of R&D people within our consortium is interested in knowing what's happening there and perhaps interacting with all the attendees today to share experiences as well. And these meetings will be nothing without our sponsors. So I would like to thank today our members Hamamatsu and Modulite. Thank you very much for your support. As in this special case, they are going also to be speakers in the meeting. They will have some time to introduce the companies and to talk more about what they do during their presentations. Again, thank you now, and we are very happy that you are here to present your solutions, and we are very interested in knowing more what's happening in your companies. And this is the agenda for today. So we can, as I mentioned, a nice set of speakers. We have two top-level research centers in Europe, the CSIC. We have Maria Vinas from the Biophotonics, Visual Optics and Biophotonics group in Madrid. And also we will have later on Carol Carnopsy from ICTER that he will join a little bit later. They are top-level institutes in the world talking about research in ophthalmology and vision. So I think it's very interesting to know what they are working on and also what they need, what they are looking for. And we will complete all the presentations with a couple of talks about lasers, the use of lasers, one of them in light-activated therapies, but the well-known company Moderator in Finland. And also we'll have Lumos Laser to talk about what's happening in precision processing of intraocular lenses. It's also a very interesting topic related with vision and eye research. And finally, we will have two presentations about components. The first one from Phaseform, talking about the adaptive optics. That is, of course, everybody knows a really useful tool. We want to know more what's happening in Phaseform and where they development nowadays. And then from Hamamatsu, Luigi is going to introduce the components for optical coherence tomography. So thank you to all the speakers that we will be presenting today. And I think we can start. So I will like first to introduce Maria Vinas. She is a researcher at CSIC in Madrid, and she's going to talk about ocular biophotonics and technologies to understand vision. So Maria, the floor is yours. You can start sharing your screen.
Thank you for the introduction. Can you see? Okay.
We see your screen, yeah, and now it's in full mode. Thank you.
Okay. Well, first of all, thank you for the invitation to participate in this epic meeting. It's quite interesting for me to show what we do in ocular biophotonics, which technologies we use in this forum, which is more industry related, right? So as Antonio said, I'm a scientist at the Spanish National Research Council, and I work in the area of ocular biophotonics. In particular, I work at the Institute of Optics, which is one of the centers of the Spanish National Research Council, and we work there at the Visual Optics and Biophotonics Lab. We work around biophotonics to understand the optics of the eye, ophthalmology, in general, eye research. So when we think of vision, and I'm going to be super brief in letting you know what is vision, we automatically think on the eye, right? And there is this analogy between the eye and an image forming in an image forming system, right? We have the images of the outer world, and they are projected on a CCD camera, which is the retina. Well, this process is not that visual. It's true that there is a part related as with a camera in which the images of the outer world are projected on the back part of the eye, the retina. But we don't have there a sharp image. We have something more like this due to the optical imperfections of the eye, and also due to the big changes that we have in the environment, changes in contrast, in luminance, in blur, in color, but also changes within the own system, right? Due to diseases, pathologies, surgery, or even corrections. So it's a bad quality image that is changing dynamically very fast. And in fact, it's the brain at the cortical stage, the one that, thanks to neural adaptation processes, we typically explain this as an instant Photoshop of the brain, the one that is responsible for us to see sharp independently of the conditions outside. So this complex process is not fully understood. And we, as you can imagine, use a variety of technologies. I'm going to show just very briefly 3 of the areas we are working right now. The first one is what happens when the camera, the eye glove, the optical system is too big. And this is what happens in myopia. The eye grows too much, and we don't have a focused image on the back of the eye. And you will say, okay, yeah, I am myopic. I know everybody who wear glasses for myopia. What's the problem? Okay, so myopia has a very high associated risk of leading to blindness. If you can see here very briefly, even low myopia leads to a significant increase in glaucoma, retinal detachment, or myopic macular degeneration. And this means that myopia is the first risk factor for blindness in the world. And the second fact that we need to remember is that by 2050, half of the world population will be myopic. So this is a really hot topic for the eye research community. And there are many areas of research associated with myopia because we really don't know the origin, whether it's genetic or what's triggering it. But we do know that the sclera plays a fundamental role. The sclera is the white part of the eye, and we are particularly interested in the back part of the eye. Okay, so because not only mechanics but also structure and molecular distribution changes. There are many technologies to understand what's happening at the biomechanical level, bibliography, airpath OCTs. We have been working with optical coherence elastography, which is the combination of an optical coherence tomograph plus an elastography technique, which basically means measuring the transmission of an acoustic wave through a certain tissue. And here you can see an example for a sclera of a porcine eye, and the difference is in the speed of propagation between a normal eye and an eye treated for myopia. And this is quite useful technology because it's non-invasive and it's already being used in humans, right? And this is a custom developed system, but I guess very soon they're going to be in the clinic. If mechanics change, structure also change. And there's a lot of people, there's been a lot of people working on structural imaging, second harmonic generation, mostly for collagen fibers. And the problem with the sclera is that it's a highly heterogeneous tissue, very anisotropic, and it's opaque. So it's complicated to do a 3D imaging stack as we want. So now we are combining 2 photon excited fluorescence microscopy with second harmonic generation to try to link molecular changes to structural changes. And we started doing that at Harvard with Fred Cho and Jun Ha-Huan using an Olympus fluo view system and also an Evintech OCT microscope, sorry. And we got very nice ideas for custom developments that we are doing around right now. So it was really a very good use of 2 complementary systems. So that's regarding the ocular optics. What happens if the camera is kind of broken? But what happens with the brain? The processor, how is the processor working? And for that, we use adaptive optics, and Tony already mentioned that. And I guess most of the people in this forum are aware of what is adaptive optics. But I would like to remind you that adaptive optics is a technology that we have inherited from astronomy, and that only in the last 25 years has been used for visual optics, and that allows us to basically control the wavefront at a certain conjugate plane of the eye, the pupil plane, and therefore we can not only characterize the ocular optics, the higher the aberrations and so, but it also allows us to manipulate. So what application has this in vision? I'm gonna just show a couple of them. So for example, we use adaptive optics-based systems to simulate very complex designs, in this particular case with an SLM, with a liquid crystal. And we can either manufacture them in terms of faceplates, or we can just simulate them on bench. And you can see here, this is a commercial design available in the market. And these are crazy designs we decided to test. And we were able to test them. We can test them using different technologies. And I will talk more about that later. And this is quite interesting for certain companies because it allows us to test any design they want to create or they want to update or test for certain patients before they're even manufactured or implanted or tested in patients. So this was really a good starting point for collaboration with the industry. An example of how this works with an industrial collaborator, for example, is how we were able to map the face map of a commercial design, the M plus oculentis, bifocal design. You can see here the two peaks, and this is the image of the real intraocular lens that is implanted in the patients. And in this particular case, we tested the through focus optical quality and visual quality on bench and using 3 different technologies, but we also were able to test them on patients. It was the first time we validated the different technologies, simulating a real multifocal design. As you can see here, the curves are very similar, although there is more noise in the subject responses due to the higher aberrations and other things. So which optical technologies, and I'm emphasizing this here because I think some of the manufacturers of these technologies are here. So some of the ones I've been using in the last years are static ones, for example, just use a faceplate or an intraocular lens next to bed, and you just look through it, through the system. There's also the dynamic faceplates, and I think this is an image from Phaseform, which have experienced a really good development in the last year. And the classical elements, which are the deformable mirror and the SLM, the DM is really a fast optical technology, and it doesn't have any chromatic effect, but it's limited in the phase it can acquire. On the other hand, spatial light modulator is a matrix of pixels, so you can achieve any phase differences you want. For example, we wrap it up to 2 pi, but it can be used up to 4 pi, but it's slower and it has chromatic effect, particularly when you want to test designs in polychromatic conditions, white light versus monochromatic. And in the lab, we developed another simulating technology. We started using an optotunable lens from OptoTune to modify the waveform temporally instead of spatially, which is what all these other technologies do. And we call it SIMBIS technology, and it's based on the temporal multiplexing of an optotunable lens, which is now commercialized by our company, Twice Vision, and which aims at be like a low-cost alternative to this more classical, let's say, technology. So how do we use these technologies in the lab? And let's see, this works. Okay, so we set up these crazy adaptive optics-based visual simulators. This is an example of the one that I developed at the Institute of Optics. We have a supercontinuum laser source that thanks to a dual acoustic tunable filters module, allows us to have two channels, a near infrared and visible one, and it allows us to have very narrow wavelengths in a very fast way. Let's let them very fast according to our needs. This will be the subject, and we have an AO loop. In this particular case, it's from Imagine Eyes. We use a deformable mirror to compensate for the aberrations of the subject. But we also have a specialized modulator to generate very complex designs. And also we have the testing channel here, a conjugate PP plane channel, where we can either place intraocular lenses next to it, we can use SIMBIS technology, or we can test whatever faceplate or optical design we want. We have a retinal camera here, which is kind of an 1.5 imaging, 1.5 system pass, and we can have kind of a PSF, the point spread function of the subject, plus the different simulations, so we can analyze the optics of the eye. And finally, we have a psychophysical channel. Here we have a DMD, a digital mathematical device, which we illuminate either with white light or light coming from the supercontinuum, and we project it on the retina of the subject through the simulations we have prepared. Okay? So as you can see, it's quite a big system. This is an image of the first stages of the development. Now it has 3 levels, I think. And our goal was to go from these big systems to clinical devices. And this is so far at the moment the final clinical visual simulator, which is not an adaptive optics based simulator, but it's an active optical based simulator. An example that I like a lot to prove the use of these active optical technologies is presbyopia. Presbyopia is the loss of the capability of accommodation of the eye. We cannot see near once we are older than 45, 50 years old, and it affects almost everybody in the world. And the thing is that not only we lose the capability of seeing near objects, but in many cases the lens of the eye is yellow, and there is a cataract there, so it needs to be changed by an artificial IOL. The designs and the differences in the types of IOLs are almost infinite. So in a collaboration with CTO, with Christophe Pagnol, and we test their fine vision diffractive design. It's this one. It has 3 peaks, far, intermediate, and vision, and it combines a refractive and a diffractive design. So it's a complex idea, and we test it on the big lab simulator, but also on the clinical visual simulator. And what we did was show what we were simulating before the surgery and test vision after the surgery when the subject already had the intraocular lens implanted. And the results were fantastic. It demonstrated that we could simulate preoperatively the vision of a patient after the operation. Look at the 2 focus curves are very similar. And in the cataract patients, we are able to replicate the behavior after the surgery, although there are differences due to those opacity. This fantastic capability has helped us to collaborate with a lot of industrial partners with different designs of intraocular lenses, and we are proud to say that we have helped in the development of some of those designs. The last example I wanna show you here is related not only of understanding how the visual system is, but also to understand what happens in the myopia process, which is how the eye grows. If that fails, we have, for example, here a myopic eye, or we have a keratoconus eye. You see the cornea is granular, right? So we know that visual information is quite important, and what happens is that the retina detects certain information, and it starts a series of molecular chain reactions, which we call the retinal signaling cascade, which at the end makes the sclera changes, the scleral remodeling, and that's why the back part of the eye is longer than it should be. So as you can imagine, this is a complicated thing to study, and this is a fantastic project we are developing with Professor Michael Celiac from the University of Rochester, where we are combining a commercial scientific multiphoton microscope with an NEA recording system, and we are incorporating a visual stimulation channel with a DMD and a synchronizable light source. And we are stimulating different ways the retinal ganglion cells to understand how they work and how we can implement those tests in humans in the visual system. So this is an example of a combined commercial devices with some tunable changes in the lab. So in summary, and I think I'm okay on time, biophotonics for eye research means for us multidisciplinary because we really need to understand and to use different imaging technologies. And what we would like to have for the projects we have right now is we are particularly interested in novel imaging tools that allows us to image scattered tissues. And we think here the focus is on the for example, phase retrieval approach is a computational approach more than optical one. We really need laser sources for multiphoton microscopy that allows in vivo imaging. I think Carol, who is talking later, will be talking about one of their developments architecture that goes in this way. So we really need more work with this. We really need to be able to acquire modular microscopes when we want to have complex spectral setup. Because sometimes what we really want is not a big work-fashion system, but we want to combine different strategies and add our own custom design. We are now working as well on nanoimaging strategies in combination with multiphoton high fluorescence microscopy, and all that only for the myopia project. Regarding the AO-based, the adaptive optics-based projects, we are very focused on polychromatic optics design. We want to help designers to design complex optics for IOLs or contact lenses that can be tested in white light conditions. And something that will help us a lot would be to have customized super continuum laser source, customized and cheap as well, because we really need something very specific, but not very powerful at the same time. And of course, we are open to collaborate with clinical and industrial partners, which is really what we have been doing always, right? Otherwise, we wouldn't move forward. And that being said, I would like to acknowledge all collaborators, which has been responsible for most of these developments, like the people at Susanna Marcos Group or Andy June's group at Wellman Center, also the University of Rochester, in other centers, and of course, current team I have in Madrid is the adaptive optics and the multiphoton team working on myopia and imaging projects. Also collaborators within the research group, particularly with Victor Rodriguez, we are working a lot in visual perception cues for myopia, which is quite an interesting area of work, and with James Sherman in all the multiphoton technologies development. And finally, of course, a network of international collaborators is essential to this kind of work, particularly one of these collaborators with which we are working very closely right now. And I guess Karen will be talking later about Kasia's work on two-photon vision perception. So that's it. Thank you very much. These are my means of my media for contact or my personal email. And if you like outreach, please take a look at this free book that we published with SPIE, and it's very funny for kids and for teenagers. And that's it. I'm ready for your questions. Thank you.
Thank you very much, Maria. So as you mentioned, we have time for questions. So you can raise your hands and make your question directly to Maria. You can also use the Q&A box or the chat box to place your question. So we have a fair question from NKT Photonics. Patrick is asking, for multiphoton lasers, which specifications do you need related with wavelength, power, pulse duration?
So you said NKT. Okay, our laser is the one that we're using right now is the bit of a Frankenstein. Originally, it was a P-anion laser, which was fantastic because it was a 4-batt laser. And after the acoustic optics and the fibers, we were in the range of dozens of milliwatts. And that was fantastic for us. The most important thing is that we are able to fine tune the wavelengths we are using in the range of 400 nanometers up to 700 or 720 nanometers. And then for the near infrared, we are more, we have more freedom. We can go out to from 800 and something, 1,000 and something, or even use only the supercontinuum for the visible spectrum. But we need a high power supercontinuum laser, a fine tuning AOTF for for wavelength selection, and a system that has to be very easy to synchronize with the psychophysics experiments and all the other devices in the system. Some of the psychophysics that we do involve, for example, selecting a wavelength, presenting an image, doing a correction with the SLN, and compare all those three with another three in a second, for example. So we need fast synchronization capability. So if you have something like that, or you want to develop something like that, we're really open to these collaborations.
Good. So I think you answered the question from Patrick, but if not, Patrick, feel free to ask again. I have a question regarding you mentioned that it would be interesting for you to have modular microscopes. What is the need behind these modularities? The flexibility for the type of tissues and samples that you are measuring? What's behind the need of this modularity?
So when we started this project, we were working only, or we were thinking only on using second harmonic generation and film, and maybe in fluorescence intensity. But as soon as we have moved forward the project, okay, we also need a confocal module. And well, also we need an in vivo platform, an in vivo stage. Oh, but we also want an ex vivo stage. And we also want to have different spectral ranges in the different modules. So it's really not only a question of building like a super crazy structure, but being able to be flexible in the sense of changing parts of the system and adapt them. For example, in retina imaging, we really need to be able to image fluorophores with a very weak signal, which are very close together. And so we need to combine at the same time SAG film, confocal microscopy, and be able to change that for in vivo measurements. So that's really the need after that.
Okay, understood. Any other question for Maria? You can raise your hands. So I do not see any question. Maria, you can perhaps place your email address in this webinar chat so everybody can contact you if they want to talk with you later on. And thank you again for being here today and for your nice presentation.
Thank you for the invitation.
Thank you. So we can now move to the next speaker. Maria already presented about adaptive optics, and we are going to learn what's happening in Phaseform with this. So we have Pouya Rajaeipour, is CTO at the company Phaseform. He finally replaced Stefan, that he in principle was the one presenting today, but it's a pleasure to have Pouya here to talk about Phaseform products. So Pouya, the floor is yours.
Thank you very much, Antonio. I'm going to I hope you can see my screen. Hi, everyone. It's a pleasure to be here. Thank you very much for the introduction and also the opportunity by EPIC. I'm very happy to be here on behalf of our company to present to you our technology. So we are active in the field of adaptive optics. Our core technology is a deformable faceplate, as already mentioned in the previous talk by Maria. And so I will introduce you more in detail what is this DPP and why we think this can bring an evolution in the field of adaptive optics for ophthalmology. So again, I think this kind of overview was also brought up by Maria in the previous presentation, but to again place our technology compared to the other existing devices for adaptive optics or phase modulation in general, I have this overview here. So we have the very well-mature perfect technologies like liquid crystal SLMs or deformed mirrors for phase modulation. Liquid crystals having millions of pixels for very high order phase modulation, or deformed mirrors also working reflection. What also existed before are these kind of tunable and adaptive lenses, which have their means of actuation outside of the optical aperture that sort of limits the amount of phase modulation, the complexity of the phase modulation that they can perform. But very good for example, focus tuning, very large amount of focus tuning. And that's where our technology comes. So what didn't exist before was kind of a refractive counterpart of these deformed mirrors, something which has like a 2D array of electrodes, but within the optical aperture, and that can provide very high order phase modulation. So here I have schematics. I can briefly discuss how it works. So there is a glass substrate. As you can see from the schematic, it looks already very similar to the continuous membrane deformed mirrors. So there is a 2D array of electrodes within the optical aperture. We have a big chamber, so it's an optofluidic device. And then there is a deformable membrane on top. And by electrostatic actuation, we can deform this membrane and modulate the optical path difference, change the amount of liquid in the optical path and modulate the phase of the incoming light. And that's by electrostatic actuation. So that's the electrode pattern of the current DPP. We have 63 electrodes, these hexagons within the optical aperture. And these are the sort of influence functions or the influence of the individual electrodes. If I actuate, for example, electrode 1, that's the sort of phase modulation which I can get. And the other electrodes, this shows how precisely we can modulate the phase of incoming light. And using these electrodes, we can replicate these Zernike modes. These are empirical Zernike modes, sort of similar to optical aberrations, up to 7th and some of the 8th order modes, both in vertical and horizontal orientations of the device. And so that's how a real DPP looks. So it's transmissive, unlike liquid crystals, it's polarization and diffraction independent. Because it's transmissive, you can even stack multiple devices together for performance enhancement. It's very thin, so the element itself is less than a millimeter in thickness. And so because of transmissivity, it also enables easy integrations and even retrofit into the existing setups. And another important factor about our technology is that it's based on wafer level manufacturing, so similar to the MEMS technologies. It's scalable, so if we need to produce a larger volume, bring the cost down by a large volume production, and that's also possible because the technology is based on microfabrication. And that makes our first product at Phaseform. So that's one of the deformable faceplate inside of a cage-compatible housing, like 30mm cage housing, driving electronics, and software. Some specifications. So as I said, it has 63 electrodes, can do more than 8 microns optical path difference. You're transmissive between 400 to 2200, and the current optical aperture is 10mm. And this product has been on the market now since 2022 in Europe, America, and multiple countries in Asia. So moving forward, what makes this technology interesting for adaptive optics? So I think Maria discussed more with regard to vision science. adaptive optics for vision science. Here I want to more talk about the retinal imaging, like cellular level retinal imaging. And as you know, our eyes are not perfect, especially, so maybe in the normal daylight conditions, when the pupil of the eye is about 2-3 millimeter, still we can do good imaging, but because of the limited numerical aperture, it's not optically sufficient to do cellular level imaging. And then when people dilute the eye, then the aberrations start getting worse, and then we are very far from diffraction limit. And then adaptive optics, of course, can be used to correct for these aberrations and improve the image quality. So this is a work, for example, by Wolf Harmoning, showing without adaptive optics for diluted eye, that's a sort of image of the retinal cells you can get, and that's when you use adaptive optics to actively compensate for the aberrations of the eye. And now image individual retina cells, that's all and good, but what would be the real interest? So this is mostly for early disease diagnosis. So these very now, unfortunately, increasing number of people are having these diseases, which are blinding diseases, for example, diabetic retinopathy subject, or you can see an AMD subject or glaucoma. And the idea is with this image quality enhancement, with this cellular level imaging of the retinal cells, we can diagnose these diseases at a much earlier stage to start the prescription earlier and avoid progression of these diseases. So this has been studied in research for a while, so more than 20 years or even more. Adaptive optics has been used to really show this application. What is it? Why is it good? But mostly because it's been very complex, expensive, and also hard to retrofit into the ophthalmoscopes, it didn't go into many commercial ophthalmoscopes. So there have been companies which made ophthalmoscopes with adaptive optics, but it's still not very, very common and doesn't exist in every clinic. And so we think that's mostly because of the complexity and cost of it. So this is an overview of how conventional AO ophthalmoscope would look like. There is a wavefront sensor to measure the aberrations and a deformed mirror or an SLM for correcting those aberrations. And so what we can do and what we want to do is to replace this deformed mirror with a DPP, which we can make it much more compact, it's transmissive, or even retrofitting the existing setups, and can make it much cheaper, and also do the aberration measurement with sensorless algorithms without a wavefront sensor to further simplify the system development. And that's what we have tried. This is a work with a group of Kate Reeve at Institut Langevin in Paris. So this is a prototype for a full field OCT setup they have built in an eye hospital. So as you can see, it's already a very compact system. And what we did was to place one of our deformable base plates right in front of the eye. So this experiment, the results which I'm going to show you, they have been achieved in 1 day. So without making any changes into the existing setup. So this ophthalmoscope existed there in the hospital. And I went there in 1 day. So we did integration of the hardware, one DPP. In fact, they also have a tunable lens for focus correction of the eye. And these are the aberrations that we corrected for. So up to 4 radial order and without a wavefront sensor. So this device had a time domain and a spectral domain OCT. We directly use the spectral domain OCT signal for the sensorless aberration measurement. And these are some results, in vivo measurements of volunteer. So here we have the DPP, the volunteer, and these are the retina cells. You can see without a DPP, so that's the resolution of the native instrument when there is no DPP in the system. And this is with DPP when we correct for the aberrations, and now we can improve the signal to noise ratio by twice and really resolve individual retinal cells. So this was a healthy eye. I think they had some eye surgeries, LASIK surgeries, but if there was some glaucoma, we could probably detect it earlier. So this was more or less the application I wanted to discuss and the benefits. We also have a Zmax model of our deformable faceplate because we consider it to be a new optical element for optics designers, for system developers to evaluate what is possible, what can be done with this technology. We made a Zmax model. It's in the form of a DLL, very much similar to a DLL of a lens, which you can insert to the Optics Studio lens editor environment. You can import it just like that. It's based on the empirical DPP, so it has characteristics of all optical layers, the membrane, the glass substrate, the fluidic chamber, and also the performance, the amount of Zernike modes that you can replicate. These are all based on a real DPP. So you can download it for free from our website. So very much encourage people to go and try to see what is really possible with this technology. With this, I come to the end of my presentation. So today I introduced you our deformable faceplate technology, a demonstration of its application in an ophthalmoscope for retinal imaging, and also the Zmax model of this device. So with this, thank you very much for introduction. We are also very open to collaborations, and I look forward to the questions. And yeah, thank you very much.
Thank you very much, Pouya. So we have again time for questions. You can raise your hand, submit your question directly to Pouya. I will perhaps, Pouya, ask you what is next in Phaseform. So you are exploring the capabilities of your solution in different experiments. Do you think it can be used in from now in handheld devices or in using in clinics? What's next steps for you?
So the current Delta 7 is a development kit based on DPP. It's kind of our minimum viable product. So what we are working on is different variants of this technology, different apertures, working on our transmission characteristics, different electrode patterns, making it more suitable for these applications. So the two areas we're active are microscopy and ophthalmoscopy. So with this MVP, we've received quite a feedback where to improve, what things have to be changed. So we are working a lot on this core technology, bringing more variables, variants, bringing more variants of this device, and also a lot on the software. So, which,
are the requirements of the ophthalmology and the microscopy very different, or they are quite similar? You can use the knowledge of the developments in one direction for the other.
I think the concept remains the same, but in terms of hardware, because what we pitch a lot is really the easy integration. And in microscopy, if you want to do easy integration, because of the type of objectives used, people sometimes prepare larger devices. Unlike in ophthalmology, the pupil size maximum can get 6.5 millimeters. So then you would need a smaller device. Or in microscopy, again, smaller strokes, but maybe more electrodes for a high order correction. But in ophthalmoscopy, you might need a larger stroke. For example, the vision science, which was mentioned by Mario, they usually need larger stroke for example, simulation of these intraocular lenses, but not very high order. So maybe till fourth order aberrations would be sufficient. So I think the concept remains the same, but the requirements are pushing in different directions.
Yeah. And how affects the light source in the performance of the DPP?
Do you mean the transmission?
Yeah.
So the current DPP is transmissive between 400 nanometer, and we have done measurement to 2200. We don't have any anti-reflection coatings on, so most of the loss that we have is because of reflections. That's biggest or one of the big developments that we do. We will soon have coatings on both glass and the membrane, and with that we can improve the transmission also quite a bit.
Okay, good. Thank you. I don't have if we have, I don't know if we have any other question for yeah, Patrick was also asking, is there a limitation on wavelengths used for the DPP?
No, no. I mean, so as I said, below 400 nanometer, the materials used, they are absorbing, but not any specific. I mean, also it's a very thin element, so we don't have that kind of chromatic aberrations, if that might be also a question. No, but not any specific limitation I can think of.
Okay, very good. So I think there is no more questions. So thank you again, Pouya, for the great presentation today. Thank you for being here this afternoon.
Of course, thank you very much for your invitation.
So we can move to our next speaker. So I would like to introduce you Luigi Ghezzi. He's technical marketing engineer at the company Hamamatsu Photonics Europe. Thank you, Luigi, for being sponsors in the meeting today. And I think you're going to present your solutions for OCT, optical coherence tomography. So Luigi, the floor is yours.
Okay, thank you for the introduction. Let me see if, as usual, all works well or not. I hope you see the screen correct.
Everything good.
Okay, perfect. So thanks, Antonio, for the introduction. And I will today describe the optical coherence tomography and what we can provide for this standard technique. Let me say, we see more advanced before in the presentation. Let me introduce quickly Hamamatsu Photonics. We are a Japanese company. It was founded 70 years ago, more than 70 years ago. We have many numbers here, but I want to highlight in particular how many products we are able to provide. We are basically a world leader in manufacturing of optoelectronics module, components, module, and system. We have more than 50,000 products that are not only detector but also emitters, and more than 2 parts of 3, so around 10,000 products are customized solution. We are able not only to support our customer in the implementation and use of our components or module or system, but also to customize the solution to help the integration or the use of the product. In this context, I want also to highlight our new pilot line that was announced during the different event that we have in Europe, the Technology Day. I think that your colleagues was joining in this, and we will have also the next one in Barcelona in June. And basically, we are expert in the components. We are expert in making prototype for the component and the optimization of the design of this prototype for creating a new product, basically. With this pilot line, we want to help all our customers that have an idea or new customers that have an idea with our expertise. So the idea is basically to collect all the possible idea for new product or new also business development, or what are all the idea that you have for the use of photonics. What we can offer our expertise in terms of the feasibility, so we can evaluate the feasibility of the idea, we can provide feedback about it, and also in case it's good feedback and feasible, also the design for it. What we don't include for sure, it's the realization of the prototypes. So in case of energy cost or something, it's something that we need to discuss with the proposal idea. But we are also in collaboration with PhotonHub for this. PhotonHub was also mentioned before at the starting from Antonio. It's one, basically they received the mandatory from European Commission to promote the new photonics idea and developments in Europe, and they can also support this new idea with some money that they receive from the Europe. So in these terms of collaboration, we can also work together in order to create your new model of the business or your idea. This is more or less the idea of the pilot line. So don't hesitate to contact us. Here there are the address. You can just write your idea and or asking to fix a call in order to discuss it and see how it works. Okay, let's move now to the real topic of today. So optical coherence tomography, it's a technique very famous, but very quickly just to remind to everyone, thanks to these techniques allow to study the condition of our eye. In particular, basically, he studied the recombination of the interference figure and the reference beam that it's collected from the eye, basically along the zeta axis. By a Fourier transform, we can catch the signal. In case we combine this with the movement on the horizontal axis, we can obtain the topography of all the eye. There are two main optical coherence tomography, depends from the light source that we are using. There are the swept source. In this case, basically, we use a light source that send each wavelength one per one in the sample. And usually the detector that are used to collect the signal are the balanced detector because they can reach the reference beam and the interference figure that it's created from the analysis of the sample, from the reflection, or the spectral domain. In this case, we can use a broadband light source, and we can resolve each wavelength by the use of gratings. Today, I want to focalize our attention in particular on this second one, so on the spectral domain, OCT. Why it's so important was also mentioned a little bit from Maria in the starting of the presentation. Today, we are starting to have an issue with the myopia in the future. It's estimated that in 2050, the half of the population will be issues with the eye, and 1 part of 10 of these maybe will have a strong myopia. The risk is also to losing the eye things. This due to the change of the routine, the use of mirrors, smartphone, and also to stay more indoors. So this is something that we need to take care and consider. And the spectral domain OCT is a very good and powerful technique to study and the health of the eye and to also check the checkup and regularity checking of our health, in particular for this part. This is the more in details, the scheme that I showed before. So we have a broadband wavelength light source. The beam is split basically in the reference part and in the beam that arrive to the sample, so to the eye. How to address this usually can be used the mirror before then all the new methods that was showed before from the other talker. And the signal, the interference signal that it's created from the analysis of the eye come back to the image sensor by a grating. In Hamamatsu, we offer components. Basically, we can offer all this type of components, the light source, but today I will not speak about the light source, but more about the linear image sensor and the MEMS mirror. As I mentioned, it's very important to the checkup, the regularity checkup. And today, one of the issues is the accessibility of this instrument, because today the instruments are very big and very expensive, so usually are not present everywhere in the world. In particular, if we think in some area that maybe doesn't have a hospital or very, very far from the hospital. Now, one of the main trends in medical is to use the MEMS mirror instead of the Galvano mirror. In this way, you know, basically MEMS mirror are more smaller in terms of complete overall dimension and can be used one mirror for the both axes in order to map all the eye. And this is an advantage not only in terms of cost for sure, but also in terms of the complete dimension of the instrument. So from the today instrument, we are moving in very small instruments that are also cheaper. And this helps to have more instruments available, not only the big hospital, but also more close to the people that need to make checkup and regular checkup and checking it. And these also have an impact on this have an impact also the dimension and performance of the image sensor that are more smaller with high performance. In terms of the sensor that in Hamamatsu we can offer for this technique, I want to mention it in particular the standard sensor like CCD and CMOS. We offer not only the sensor but also module that easily integrate this sensor with an easy communication. So we already provided the electronics to drive the sensor and to catch out the signal. We are able to offer also in-gas sensor in case we want to use more infrared detection, and the balance detector that are usually used for the SS or CT. What are offering new compared to the linear lineup of our product? For the sensor, basically, we are working on this new sensor module that will be available soon that integrate our CMOS. The sensor inside have a dimension of the pixel of 7 micro for 200 micro with 1000 pixel with an high-speed readout and a mobile industry process interface. This module can be provided with the anti-reflection coating or without the window. But we are also working on a new sensor that it's basically included in this module that will be released soon. This new sensor will have basically the double of the pixel compared to the existing one, but will able also to provide the double of the speed readout. So we are able to arrive to 61 kilohertz. There is also another advantage in this new sensor. We are able to provide the function called 2-pixel binning function that basically allows to increase the pixel readout with the reduction of the pixel. If you don't need 2000 pixel, but you can use 1000 pixel, basically you can reach a readout of 100 kilohertz. This module will have the electronics to drive the new sensor and also the possibility to be connected by an USB 3.2, so it's very easy to connect. In terms of the MEMS mirror, actually we are able to provide these 3 MEMS, in particular the resonant on 2 axes or the linear on 2 axes. But what I want to show today to you, it's also this new MEMS mirror that will be available soon. This month, honestly, in June, so very, very soon. And what we are realizing here, we increased the mirror size, so we arrived to 5 millimeters with the usual optical deflection angle that is plus minus 10 degrees on both axes, with a good frequency, 100 hertz for the primary axis and 50 hertz for the second axis. So, in conclusion, thank you for listening. And again, here this is my email if you want to have more information about this new product. And here the email of the pilot line that I tried to describe you at the starting. So thank you for listening.
Thank you very much, Luigi. We have time for questions for Luigi. I will perhaps start with the typical EPIC questions. You told us what can you do for the others. What can other members do for Hamamatsu in this particular case of these detectors? You can perhaps tell us a couple of things.
For sure, we provide the components. So, basically the request that the customer can have, also the challenge that they can have because they are the end user and they know better than us the challenge that there are in the application. It's all welcome received from us, and we try to provide the best. So in these terms, for sure, challenge or idea now with the pilot lines.
Mm-hmm. Yeah, it's a good policy. How was the pilot lines in the other cities? Were they successful in terms of attendees and discussions?
The technology day that I mentioned was very good. Attendance was honestly not only pilot line, was pilot line and capability of Hamamatsu. So we show, that we have this big event in Japan every 5 years, and we take some videos and take some technology from the event. So we also show our capability, but was very positive feedback from the customer.
Very good.
The next one will be in Barcelona if you are close.
Yeah,
we wait for you.
I saw it, so I took note already. I will check the agenda.
I will be not there, unfortunately, but my colleagues will be there. So
perfect. I took note. I don't know if there is any final question for Luigi. If not, thank you again for being here today, and thank you also for being sponsors. And yeah, it was a pleasure to look at your developments in Hamamatsu.
Thank you to you. I want to stop the okay, it's here.
Yeah,
I don't see where it's.
you have big screen there.
Move on the second mirror, so okay.
Thank you,
Thank you.
Luigi. And let's go with our next speaker. So it's a pleasure for me to introduce you, Laura Besala. She's R&D engineer at Modulite, and she's going to present the solutions and innovations in light activated therapies in ophthalmology. So Laura, the floor is yours, and thank you also to Modulite for being sponsoring the meeting today.
Thank you so much for the introduction. Here, let me share my screen. Okay, let me know if you can see my screen.
Yeah, everything good.
Perfect. So hi, everyone. My name is Laura Vasala, and I work as an R&D engineer at Modulite. Thank you so much for having me here today to present to you our company and what we do in the ophthalmic domain. So without further ado, let's get started. First, I want to give you a quick introduction into Modulite as a company and who we are. Modulite is a laser manufacturer based in Tampere, Finland, with a sales presence in the US. The company was founded in the year 2000, thus we have over 20 years of experience in various laser technologies. In 2021, we were listed in NASDAQ First North Helsinki. Our mission is to kill cancer with science and technology. With this, we are probably best known for our work in life sciences and more specifically in our key strategic areas of oncology, ophthalmology, genetics, and diagnostics. In addition, we also have service offerings which are mainly built around medical devices where we provide on-site trainings and regulatory as well as lifecycle support for the products that we offer. We are a vertically integrated medical laser company, meaning we do semiconductor laser design and manufacturing in-house, as well as building complete laser systems. Now, I will show you a short video showcasing our factory.
We do lasers and optics for personalized medicine and better life.
Modulite is a unique vertically integrated company. Our mission is clear: kill cancer. We design and manufacture tailored lasers for demanding applications, from closely regulated medical treatments to flow cytometry and even quantum computing. Everything is crafted in-house, from epitaxial structures and custom mechanics all the way to clinical devices. Our full vertical integration ensures unparalleled control over supply and change control. Our cloud-connected devices offer preventive maintenance and predictive analytics, keeping your technology ahead of the curve. Let's dive deeper into today's presentation. Follow Modulite for more insights and innovations.
Okay. As the topic of today's presentation is light-activated therapies in ophthalmology, I want to first start off by discussing causes of vision loss. Even though vision loss can affect people of all ages, most people with vision impairment as well as blindness are over the age of 50. Thus, with people continuing to live longer, the number of individuals suffering from visual impairments as a result of age-related diseases is increasing globally in numbers. Some of the leading causes of disease-related visual impairment are identified as cataract, diabetic retinopathy, age-related macular degeneration, and glaucoma. Here, I'll dive deeper into age-related macular degeneration. Age-related macular degeneration is characterized by the development of choroidal neovascularization and consequent irreversible damage in the macula. AMD is one of the most prevalent causes of irreversible central vision loss in the elderly population. CNV is the development of new blood vessels, also known as angiogenesis, from the choroid into Bruch membrane, sometimes capable of even perforating the retinal pigment epithelium. Thus, when the retinas of patients with AMD produce excess vascular endothelial growth factor, these new blood vessels emerge from the choroid, then into the retina. The new vessels, unlike normal ones, are leaky, and they allow fluid from the blood to enter the retina, resulting in vision loss. AMD is classified into two categories: dry AMD and wet AMD. Dry, also known as atrophic AMD, is the most common form, which then typically develops into wet AMD. Dry AMD is non-neovascular and is defined by retinal pigment epithelial abnormalities as well as drusen. As mentioned, the processes Process of AMD typically starts with dry AMD, which then develops into wet AMD when these aberrant blood vessels form behind the retina and begin to cultivate beneath the macula. Wet, also known as neovascular or exudative AMD, is less common but results in faster vision loss. It is the leading cause of blindness in people over the age of 65. The first-line treatment for wet AMD are anti-VEGF injections. However, photodynamic therapy is a good treatment option for patients who do not get satisfactory responses from anti-VEGF agents. This makes up about 25% of the patients. When discussing the global prevalence of AMD, both wet and dry, it is predicted that by the year 2040, the sum of patients affected by AMD will reach up to an astonishing 288 million. Wet AMD accounts for about 10% of AMD patients, but results in 90% of AMD-related blindness. Next, let's discuss a little bit about another serious disease, ocular cancers and tumors. I actually just got back from the EURBG conference where I had the pleasure to listen to ocular oncologist specialists share their knowledge as well as experience in the field of ocular oncology. So what is ocular oncology? Ocular oncology focuses on diagnosing and treating both benign and malignant tumors located in or around the eye. These tumors can form on the eye's surface, the eyelids, or within the eye's tissues. They may originate from the eye itself or metastasize from cancerous tumors in other parts of the body. Ocular cancers, though rare, pose serious health risks and can affect one or both eyes. The likelihood of developing ocular cancer increases with age, particularly after the age of 50. Benign eye tumors include choroidal hemangiomas and retinal capillary hemangiomas, where the treatment options include PDT, photocoagulation, and transpupillary thermotherapy, just to name a few. Malignant eye tumors, on the other hand, include choroidal melanoma and choroidal metastases. Choroidal metastases is a source of cancer which has originated somewhere else in the body and by means of blood flow has spread to the eye. The majority of choroidal metastases in women originates in the breast and for men in the lung. Treatment options for choroidal metastases include PDT, external and proton beam therapy, as well as plaque therapy. Moving on to choroidal melanoma, as most uveal melanomas originate in the choroid, they can also be called choroidal melanomas. Choroidal melanoma is the most common primary intraocular cancer in adults. Treatment options include radiotherapy, enucleation, which is the removal of the eye for larger uveal melanomas, and currently PDT has also been viewed as an attractive treatment modality. As we can see, for many of these diseases affecting the eye, PDT is an attractive option. Next, I will go more in detail regarding the overall mechanism of PDT. So here I have a quick overview of a typical photodynamic therapy procedure. First, the patient receives an administration of the photosensitizing agent, typically as an IV injection. The photosensitizer is metabolically distributed in the body to cancer cells or accumulates in abnormal blood vessels, as in the case of wet AMD. This photosensitizer is then activated in the presence of an external light stimulus, in other words, a laser. Laser light is absorbed by the photosensitizer to activate the drug molecule. Primarily, the photosensitizer is in the ground state, and once irradiated by light, the photosensitizer is transformed into an excited state. Thus, the photosensitizer working principle is that the laser excites the photosensitizer to a higher energy state, and with the subsequent state transition, the oxygen in the tissue is transferred into ROS, also known as reactive oxygen species. The ROS produced in the tissue is attacking the tumor or vascular tissue. The cells die by necrosis and apoptosis, and the body's immune system takes care of the rest. So what are some of the benefits of PDT over other treatment modalities? Some advantages of PDT over traditional cancer treatments include it enables highly selective targeting of cancer cells. It is a minimally invasive procedure which effectively treats tumors while preserving healthy tissue. It has reduced side effects compared to chemotherapy and radiation therapy, as well as it provokes an anti-tumor immune response in the body and can work by shutting down microvessels as seen in the case of wet AMD. PDT in ophthalmology has been around since the 1990s. Here on the left, I have a schematic of an eye with healthy retina, choroid, and RPE cells. Then right next to it, we can see the effects of AMD, where there is a presence of early drusen and neovascularization, which results in the disruption of the Bruch's membrane and RPE cells, as well as vascular leakage. As in the case of wet AMD, the drug remains inactive in the vessels until exposed to light energy. A red 689 nanometer laser light is delivered to the retina in a controlled manner, and this light exposure in the choroidal neovessels will activate the drug to initiate vessel occlusion. This is the basic PDT mechanism seen in the treatment of wet AMD. Here we have an overview of the vascular effects of photodynamic therapy. The PDT-induced free radicals are concentrated around the walls of the choroidal neovessels, which leads to a series of events including vasoconstriction, blood flow stasis, and thrombus formation, resulting in vessel occlusion. Photodynamic therapy in wet AMD slows down central vision loss. I also want to mention that when it comes to ocular oncology, there are novel drugs being developed which harness the mechanism of tumor targeting. In other words, after the drug is given to the patient and accumulates in the tumor, the specific region is then illuminated using laser light at a specific wavelength to activate the drug to cause tumor necrosis. In ophthalmic applications, PDT is utilized in the treatment of various ophthalmic diseases. On the lower right-hand corner of the presentation, we have a QR code which you can scan to check the list of studies and publications which we have collected on ophthalmic PDT treatments. Just to briefly mention, photodynamic therapy utilizing Visodyne is FDA approved for predominantly classic subfoveal CNV due to AMD, myopia, or presumed ocular histoplasmosis. As mentioned, wet AMD is a significant cause of vision loss worldwide. PDT as an off-label treatment modality is being utilized in clinics for the treatment of ocular diseases such as central serous retinopathy, PCV, and various indications in ocular oncology that I've mentioned. Modulite has developed solutions to ophthalmic indications for over 10 years. Especially our product platforms of the ML7710 and ML6710i have been used in ophthalmic treatments. We have developed the ML6710i based on the need from the market and for the doctors and patients. The need was and is to replace old and obsolete laser systems that are not being supported anymore. In 2018, Bausch & Lomb chose Modulite for their exclusive partner for developing a new, novel ophthalmic laser to be used with their pharmaceutical compound Visodyne. The ML6710i laser for Visodyne treatments got the FDA approval finally in early 2023 after a quick development project and thorough usability testing, not to mention all the regulatory work required. The FDA approval covers the wet AMD indication with Visodyne, and the drug is marketed in USA by Bausch & Lomb. Here you can see our modern and fully supported ML6710i laser. It is controlled intuitively through means of an iPad application. The laser is connected to our Modulite Cloud platform, which enables all the operating parameters and laser on, off, pause events to be safely stored into the treatment log. The laser light is formed into a uniform circular spot by the Modulite laser beam shaper, which can be attached onto most common slit lamps. On the right-hand side of the screen, you can see some of the great feedback we've received from ophthalmologists regarding our laser device. As mentioned, the ML6710i laser device is cloud connected, which enables the user to tailor their account to their liking, enabling their, for example, enabling their favorite contact lenses. They're also able to view the treatment history and to view online tutorials whenever needed. In addition, this cloud connectivity paves the way for software updates and support for the pay-per-treatment model. In the figure on the right, you can see the benefits of our Modulite cloud. Having all the Modulite lasers in the field connected to our cloud service allows us to have real-time information on their status. For example, we can prepare for preventive maintenance and have everything arranged with the clinic in advance to make the process as smooth as possible for them. We can monitor the laser performance and detect possible incidents compromising the output, such as possible impacts on the fiber in the clinic, or predict unexpected laser degradation. As mentioned, we're offering a pay-per-treatment model where the clinics only pay for the treatments performed. The treatment charge then includes ongoing support and services. I want to summarize everything that I've talked about in this presentation in 3 points. First, there are several diseases that affect the posterior portion of the eye where PDT is an attractive treatment option. 2, Modulite's modern cloud-connected ophthalmic PDT laser brings PDT therapies to this decade. And lastly, the platform design enables utilization of the same hardware for multiple indications, widening the install base and scope of use. Then I want to end the presentation by answering the questions of what can we do for you and what can you do for us? What we can do for you is deliver complete, tailored treatment solutions such as in ophthalmology, which I have discussed here today. We can ensure long-term supply of critical laser and optic products from our own factory. And lastly, we can provide you with services such as installations, trainings, and biolab service for your research and development needs. Then what can you do for us? Is you can partner with us to deliver precision parts for medical devices, as well as integrate your biomedical expertise into our products. And with that, I want to thank you for your attention, and please feel free to follow us on various social media platforms. Thank you.
Thank you very much, Laura. So we have now time for questions. We already have one question in the Q&A box from Samuel. Could you provide a list of clinical papers?
Of the clinical papers in the PDT and ophthalmology? Was that the question?
Yeah, that should be perhaps a question to discuss further on. Perhaps I can put you in contact by email and you can discuss later on.
Yes, that sounds good.
Of Samuel. I have one question regarding the use of the your laser by the ophthalmologist. How they because it's mentioned that they can be used for different kind of treatments. So how they adjust the parameters of the laser depending on the treatment? Is there any kind of recipe that you establish for the different treatments based in your previous studies? Is more the experience of the ophthalmologist that know more or less how to use this solution? Can you tell us a little bit of the use of your laser?
So it's more of the ophthalmologist, like their decision making, but as I mentioned, the user interface of the laser is on the iPad. So on there, you can select your desired treatment parameters, such as the dose and the irradiance, as well as select the specific contact lens that the ophthalmologist wants to use. Because what we've seen is that ophthalmologists, they prefer different types of contact lenses and everything like that. But one of the great benefits of this laser is that in the iPad, the ophthalmologist can select their specific contact lenses in the My Lenses section, and those will be enabled onto the treatment parameters page where they can just click the drop-down menu and select the specific one they want to use.
Okay, good. We have also one question from Patrick Koch from NKT. Patrick, I don't know if you can do the question live.
Let me see. I hope you hear me.
Yeah, we can hear you.
Yeah. Hi, Laura. Great talk. Thank you very much. That was really interesting. I just wondering for the PDT treatment, is there is non-specific binding a challenge, and do you overcome this by targeting specific sites with a laser versus, let's say, wide field illumination?
So what you're asking is how the laser would work in a clinic. So what would kind of happen is that the ophthalmologist would use a contact lens to find the specific target in the patient's eye and at the back of the retina. And we have an aiming beam on the laser so that they can find the specific area first before they actually do the treatment itself.
Okay. Thanks.
Thank you.
Is there any other questions for Laura? Well, if not, thank you again for the great presentation today, and thank you also for being a sponsor of our meeting from Moderator.
Thank you.
Thank you, Laura. So we can move now to our next speaker. It's Altan Yildirim. He's the CEO at Lumos Laser, and we are going to talk about lasers, but now in processing materials. So how to use ultrafast laser for precision processing of intraocular lenses. So Altan, the floor is yours. Do you want to try to share your screen, or should I do it?
I will try my
Okay.
chance. I will try to skip the videos. So thank you for the introduction. Can you see my screen now?
Yeah. Not in full mode yet, but okay, now it's working well.
Okay, so there is some delay. So good afternoon, everybody from Istanbul, and all the delay is caused by Istanbul and 34 degrees weather probably. So sorry for any inconvenience. So I would like to thank all the speakers and the EPIC team for this organization and for letting us take part in this. And I really congratulate you on your efforts creating nice ecosystems for networking. So I'm going to talk about Lumos Laser today, our innovative gigahertz burst femtosecond laser technology, and also how we use these lasers in processing intraocular lenses. So maybe you all know femtosecond lasers are already applied in the industry, especially in consumer electronics. Every smartphone has several to tens of parts being produced by femtosecond lasers. Also displays and mechanical components, medical devices such as stents, automotive components. You can see several nice examples here. Very innovative applications were found with femtosecond lasers. Also medical applications like any kind of surgery at the moment, but especially LASIK, the eye surgery and vision correction. But there are also a lot of emerging applications, such as the precision glass processing. Glass is a delicate material, difficult to process. So femtosecond lasers are really creating promising applications there, such as microfluidics or selective coating removal over glass without disturbing the glass. Also other medical treatments and other medical devices like IOLs and cochlear implants, or tissue processing is also on the way. And on the energy side, photovoltaic and fuel cells, batteries all have quite application fields to femtosecond lasers. But due to the very low energy and very short pulse times of femtosecond lasers, there is also a lot of opportunity in spectroscopy, for example, or neuroscience or bioimaging as well. So there are challenges in front of the realization of these emerging applications. The problem is the industrialization, actually. There are a lot of proof of concept studies, but to bring these to industry is always a challenge. Every industry has different standards. Medical I guess the best, one of the highest standards. So biggest challenges in front of femtosecond lasers are speed and cost challenges, both initial cost and running costs. So Lumos Laser has developed the gigahertz burst technology and published it in year 2016 in Nature. Actually, and those times Lumos were actually spinning off from Bilkent University, Professor Ilday's group. And so we really have a completely new laser design. It's offering 3 to 10 times higher material processing speed. It has a low power architecture, so it's a simpler laser device. Therefore, the costs are much lower, and it's up to 80% energy saving. So in summary, we have a new femtosecond laser technology, which has higher machining speed and simpler system design in summary. So how is this possible? If you want to increase the micro machining speed in a femtosecond laser, you need to put more energy into single pulses. But after some point, this energy transforms into heat in the material and other plasma and other physical phenomena, so that you only have some part of this energy going into the ablation of the material. So instead of putting high energy, Professor Ilday's group has developed a gigahertz burst regime, which totally created a new mechanism of ablation, which is called cool ablation or ablation cooling. You can see the article if you want to read. So instead of high energy single pulses, we can use much lower energy pulses at a gigahertz repetition rate in bursts. So instead of one higher energy, we have a lot of low energy pulses as femtosecond pulses. So you can see in the demonstration, I hope you can see. So with gigahertz burst, it goes much faster, actually, without heating the material. An alternative study is also being conducted in several research institutions that to have a very high energy femtosecond laser pulse and split it into many parts and micro machine many components at the same time. So this is also another approach to speed up the femtosecond lasers, and they are all in investigation, under investigation by many groups. So you can see here, we have shown here, with respect to uniform femtosecond lasers, we have at least 3 times better line scribing efficiency in all of the materials, and our results are also in good correlation with the literature. And so we decided to bring this technology into life and started Lumos Laser in 2018 as a startup company, and we are still a startup company actually. In Boğaziçi University Technopark is our location in Istanbul. So after preparing our prototype in the laboratory, it's a demonstration laser, we have proven several POCs. We have completed several POCs, and then in 2021, after collaborating with a lot of partners, mainly in Turkey, but also many global partners, we have developed our first gigahertz burst laser in 2021. We have delivered it to Eskişehir University. Also in Turkey, there is a group there working on metallic materials and also magnesium spinel glass to be used for watches or cell phones in the future as an alternative to sapphire glass. So we successfully machined those materials, and our system is at the Eskişehir Technical University at the moment. Another very interesting project was together with FH and W in Switzerland with Professor Boyan Resan together. We have developed a dual mode laser working both in gigahertz burst and uniform femtosecond machine. Also, it's being used for research and metallic materials processing. So the next, we are now working on two lasers actually after developing these first two. We are now developing our high average power laser for, again, research and research applications and coating removal over glass. And there we are working with Bilkent University and Şişecam, which is one of the largest glass producers in the world, which is located in Turkey, has over 25,000 employees, I guess. So we have a nice collaboration there. And today's topic is our next laser, actually. Today I will show you more on that, about polymer processing together with VSY biotechnology, processing intraocular lenses. So we had many collaborations. We had many more, actually. I just selected some of them. But we really caught nice opportunities, and we are very open to collaborations. We proved that, I guess, and in the global arena as well. So, can you hear me still?
Yeah, we hear you. Was a short delay, but now we see the screen again.
Okay. So in the end, this is how our product looks like. Of course, we develop it with time. It's under continuous development. I have to say, we are the experts on creating femtosecond laser bursts. These in gigahertz frequency. We develop our own oscillators, our own control systems, softwares, electronics, and everything, and hardware as well. So in that sense, I'm really proud of what we have achieved today. So this is our up-to-date laser. We have a really good beam quality and nice pulses. You can also check our website for more. So coming to today's topic, I'm going to talk about our collaboration project together with VSY Biotechnology and Boğaziçi University. VSY Biotechnology is offering intraocular lenses, monofocal, enhanced depth of focus, or trifocal, or others. And they are already producing them. They have very innovative lens and optical solutions, also from the material. And an intraocular lens has an optical part and the haptics. Optical part is responsible for sight correction, of course. First of all, the cataract removal and, of course, the vision correction. And haptics are also very important to hold the lens in its place, because we remove the original lens and put in this implant. And it's a very delicate medical device. And here you can see a multifocal lens. It has these diffractive Fresnel rings on it, which creates this multifocality, actually, which is a very good, it's a patented design of VSY Biotechnology. And we are trying to reproduce it with laser, which is already being produced mechanically. However, the mechanical production has a lot of steps. So it includes molding, cryogenic cooling, and then cutting, and then cleaning, a lot of steps. And with laser, you can do it in one step. So it seems quite feasible when we will see, of course, that after our project closes, but it's a really promising technology. So some of our results, I will try to play this movie at the end of my presentation. So so you can see we have optimized the laser on polymer material and tried have some laser optimization. After finding the perfect parameter, then we have created the Fresnel rings also. We have machined them on the surface. And you can see we have quite nice patterns which are very similar to the original one. Of course, we have some more optimization work to do, and I cannot give any more details here because this is a study and there are 2 PhDs and it's an ongoing research. After we publish, we can present much more, probably. And here you can see the whole lens having after laser patterning with the Fresnel lenses. And another interesting application is also we can see the result after patterning the lens. This is a monofocal lens you see here. After patterning it, we had the first a monofocal lens, as you can see from the MTF curve, dioptry 21. So after putting on the Fresnel rings with the laser, now we have an enhanced depth of focus. And these type of lenses, intraocular lenses, are getting more and more popular because it's a bonus for a monofocal lens. It makes you see a little bit more. So it's together with the neuro adaptation, it's really giving quite a promising result. Here you can see some of the rings, I hope, from the picture. And in addition to optical processing, we are also cutting the lenses for the production. And we also have completed our first trials and optimizations. And the speed here is very important, which we are really improving. And also the quality is very important. It even affects the vision because after the lens being cut, you want to have very sharp edges here, only in the optical part, of course, to hinder any other reflections and so on. And to have a clear vision, we really need to have very clear cuts, and we are still working on it. Oh, now the movie is playing. I hope you can see. Okay. So I am impressed and I'm going back to play this one as well. Can you see that as well? Okay, perfect. So this is how we machine the lenses. So coming to the end, what do we offer? We have turnkey gigahertz burst femtosecond laser modules. We can customize them to the application. We have a talented team of ultra-fast laser experts and talented engineers. We like to collaborate, and we have completed many POC studies on new materials to find new applications. So what we are missing is actually a very strong partner for technical collaboration on material processing, because we are experts on the beam, and there is also a lot to do on the material processing side. Playing with the beam and putting it on the material is also another. I mean, it's open for innovations. It can bring a lot of innovations. So we are more on that simple side, and we are looking for R&D partnerships in any form for new application development. And still as a startup, we are also looking for investment opportunities. Thank you again for having us here today.
Thank you very much, Altan, for showing the presentation, and thank you for the videos that finally worked.
Yes, yes.
We have time for questions. I would like to start first with a question because you briefly mentioned the beam quality, but I would like to have more details about the beam quality with this gigahertz burst solution. Can you have a laser with a lower quality beam to get good results using this burst technology, or is the material glass that require really higher beam quality, even if you are using this burst technology, or they are independent? So you need to have both at the same time.
Well, I think it's always advantageous to have the best beam quality because it's just the beginning. After you can play with the beam, and then it gets anyway challenging. So at the output of the laser module, you need to have a perfect beam, as good as possible. I mean, the beam shape. In our case, the trouble is, I mean, for gigahertz burst, everything is ultra fast. The electronics control units. So you have seen the burst envelopes. They also have to be perfect, but not as perfect as the beam itself. So beam really have to be very good quality, but it depends on the application. But gigahertz burst doesn't change that.
Okay, yeah.
But if you have a non-precise application or maybe more superficial application, maybe you can use that. But everyone prefers a good beam quality.
Yeah, I was thinking if this avoiding the heat process, perhaps you can also play the same kind of structures without the beam quality. But it's true that it's not a pain in the ass to have a beam quality. It's always advantageous when you have already.
Yeah, I mean, in the lab it's fine in the lab, but if you are in the market trying to make it a validated product, I guess it's not so.
Yeah. Patrick, we have a question from you.
Yes, let me see if I get this started here.
Yeah,
Hi, Alton. Thanks
Hello.
again. Great talk. I was
Thank
just
you.
wondering a little bit more about the specifics of the laser. Let's say which wavelength you used. If you use an SHG module or just the fundamental. Maybe a little bit about average power or pulse durations.
Yes, actually, I had a slide, but I was very quick on that. Here you can see every detail, actually.
Oh,
Let me know if you cannot find anything. So we have 1030 nanometer.
mm-hmm.
We have a fiber laser, 30 watt average power, up to 6,000 pulses inside burst, and 4 gigahertz repetition rate. We can adjust the burst shape, and up to 150 microjoule burst energy.
Mm-hmm.
Anything else you want to know?
No, perfect. Sorry, I missed that.
No, I skipped that quickly just to be in time. And you can check our website for other laser modules as well. Yeah.
Is the generation of then let's say green at 515, is that a challenge with the burst mode, or is that similarly possible?
It is possible. You said 515, right?
Yeah, so just the SHG output, let's say.
Yes, it is possible, but we are not focused on that at the moment. But we have a project on there as well. It will be coming, I guess.
Okay.
We stick with the burst optimization, and since we are focused on the product quality and product maturity, reliability, everything is quite an effort for us as a startup. So we are at the moment 1030, but we had projects with 515.
Thank you.
We have final question from Samuel from Imagine Optic. He's asking, why not using adaptive optics to manipulate the spatial shape of the beam?
I couldn't get the question. Sorry.
Yeah, he's asking, why are you not using adaptive optics to manipulate the spatial shape of the beam?
We are using that, but as I said, we are more focused on the laser module, not on the processing side, actually. So we are open for any suggestions in that sense. So of course, it's a correct suggestion, but it's not in our focus to play on that side much.
Okay, understood.
Yeah.
So thank you. I think it's the last question. So thank you again, Altan, for the great
Thank
presentation
you very much.
today. And let's go with our last speaker. So we have Karol Karnowski, Senior Researcher at ICTER, and he's going to present the eye research lines. Karol, thank you so much for today in being here and sharing your research with us this afternoon. So Karol, we are seeing your email now. You are muted, so you need to go down to the left to the microphone.
Okay, now it should work.
Now it's working. Thank you again for your effort in being here this afternoon.
Thank you. Thank you very nice. Thank you very much for invitation. So I will be talking about the research related to eye, and because it's like photonic meeting, I will be focusing on the optical techniques. So we are International Center for Translational Eye Research, and we are part of the Institute of Physical Chemistry, Polish Academy of Science. The center was established within the International Research Agenda program from European Union, and we already received this funding twice. This year we started second phase of this. So before I start going in a little bit of details about the optical parts, let me introduce the center itself. So we have 5 groups. First group, Physical Optics and Biophotonics. It's led by Professor Maciej Wojtkowski. And this group is focused mostly on developing novel imaging modalities. And you can see here the schematic of one of the systems that is, we believe, another generation of optical coherence tomography methods, and colleagues call it STOCK-T. When they acquire images, volumetric images of human eye elements very fast with very good accuracy. So then we have image-guided devices for ophthalmic care group, and I'm acting PI in this group currently. The former PI, Dr. Andrea Culatoro, moved to Milan for the professor position. In this group, we are focusing on to study eye function and also to monitor various eye treatments. Also around eye surgery planning, eye surgery guidance with optics. And at the end, we would like to also focus a little bit on a low-cost solution. And I will also say a little bit about this later on. We not only have optical groups like imaging groups or kind of technology groups. Dr. Beto Fernandez is leading integrated structural biology group, and they are working on various proteins involved in the vision cycle and how to use them to improve things, maybe learn something fundamental about the vision process and what's happening in the retina, and also provide some therapies. Another group of this kind is Ophthalmic Biology Laboratory, led by Dr. Andrzej Fojk. And the focus is to work on various mouse models to study the vision both in eyes and brain. And for example, he is trying to use rabies virus as a kind of delivery tool for therapies. And the last group is computational genomic group, and PI here is Marcin Tabaka, and they work do a lot of experimental and computational studies on single cell transcriptome, and epigen profiling. So I'm not so familiar on those biology parts, so I will focus on optical. And a lot of activities in the center actually is driven by some of the work of Chris Palczewski, who actually was involved in the first international research agenda program that we received. And he's working on the gene therapy for various eye, like vision conditions. So he believes that in a decade, it will be possible to cure a lot of them with these new technologies. And because those technologies are approaching, it's important to do a lot of things around them. So let's say how to deliver the treatment to this specific regions of the retina, and how to define to which region we should inject this gene, and also to study the not only the structure of the eye, but also the function. So let's go back to POB group, and the group developed. The method was developed over almost a decade now, I think, and it's called spatial-temporal optical coherence tomography, and it's kind of holographic OCT. So the images are acquired in full field scheme, so all pixels are acquired at the same time. It's demanding for the camera, and I will mention this at the end, and it requires slightly different light sources that we normally use for scanning spot OCT. As you can see, they can really collect very nice high-resolution images of the retina and also of the cornea. And they use some tricks to play with coherence of the light that is used in the method. For instance, this helps to reduce crosstalk from the deeper layer, which is usually drawback of such techniques. So they show that with this crosstalk reduction, they can really, I think, probably for the first time, image the choroid layers and then study choroid capillaries in detail. Because the technique is very fast and it's acquired in kind of full field fashion, we have very stable phase along whole plane of that we are imaging, and that allow us to use phase sensitive methods. For instance, you can apply some stimulus to the eye, like in this case, colleagues applied flicker stimulus with this kind of stripes, and you can see on the left that we are able to recover these tiny changes. Those light-induced changes in the retinal layers are at the level of few or tens of nanometers, which is we can measure very tiny changes in the living eye. And all this, like this functional imaging, will also be important to study whatever those gene therapies are really doing what they should do with the retina in the mission of preserving the vision. We also have some fancy things that were probably, I believe some of you will not recall that something like this is possible. In terms of that, we can see infrared light in specific condition. If we have laser that is pulse laser, and I think in this case, you need at least nanosecond pulses in the range of 900 to 1200 nanometers, you can perceive light that will be roughly equivalent of second, like two-photon effect. So let's say it started when we've been using 1060 swept laser for retina imaging, and when we align the patient, we usually scan the eye in the kind of cross fashion, and we perceive the green cross, which is kind of not intuitive why we see it. And then Kasia Komar, who is leading this part, did a lot of work to really study how this works for different wavelength in this region. And it's very promising because it looks like that this technique might be more sensitive to study some kind of quality of vision than equivalent studies done in visible range. So they are still exploring this. And there are some other aspects that I cannot mention yet because they are kind of patent pending. But hopefully in future we'll be able to share it. The other part with this 2-photon process is that we can, my colleagues show for the first time in humans that you can use 2-photon process to do kind of laser scanning of ophthalmoscope. So they kind of develop the system. The signal is pretty low, but you can do averaging of multiple frames that are aligned based on classical techniques. And this technique is really explored with our group and also Chris Palczewski and his wife, Grażyna. So for IDOC, interoperative devices ophthalmic care group, part of the work is to add some optical components to surgical kind of scenarios. In this case, what we can see is the screen of the combined panel. We see the view of the standard view of the surgical microscope on the top left. So you see artificial eye and the needle. Close to it, you see two grayscale images. These are OCT images acquired. One is along the needle and the other is perpendicular to the needle. And the idea is here to track the needle and display those preview images. So those will give you additional depth information for the surgeon, which is missing in the classical approaches. And you can track the needle by vision means, so we can acquire images from the camera and do some kind of on-fly segmentation of the needle, maybe with machine learning. Or in this case, we decide to place the tool with the needle on the wrist of the robotic arm. And if everything is calibrated well, we can send the information from the robot about the position of the end of the surgical tool to the OCT software. And on the fly, in this case, it's 200 Hertz refreshment rate. We can update the scanner pattern that is used to scan this B-scans along and perpendicular to the tool. So this is our fresh result that we are drafting the paper on. And the other example on this, and it's also close to the clinic, there is this technique for tonometry measurements when you apply air pulses to the eye. And probably some of you may have those measurements done in the ophthalmic clinic. And then you have infrared light illuminating the cornea, and you measure the amount of light that is reflected from the cornea's surface. So this is in this kind of standard clinical measurements. However, in this case, you do this measurement indirectly. 10 years ago, we proposed to combine this air path stimulation with the OCT, so we have direct measurement. And we did it only for the central point at the cornea. Of course, the cornea pathologies, for instance, like keratoconus, they don't occur central symmetric. So we'd like to probe more points. We did some work with Andrea Curatolo on the multiple meridian approach that you can acquire those corneal deformation at 1 kilohertz. But I believe that you need better temporal resolution because the process of deformation recovery is like around 20 milliseconds. So what we developed here, and you see on the left clinical prototype that went to clinic and measured size, more than 100 eyes already. We have multiple spots distributed along the cornea surface, along main meridians. And with current OCT technology and light source technology and digitizers, we can acquire all those points simultaneously simply by adding some phase delay to each channel. And in the middle, you can see an exemplary image of such deformation measured at 9 spots simultaneously. And just to give you some hint, we are working on big paper on this, so I cannot share full details. From this clinical measurement, we can show that some parameters extracted from these deformations give us ability to nicely separate a control group from a keratoconus group. So this looks very promising. And here we hope that in future we'll be able to translate this device to more advanced product that will be possibly handheld, and this requires some additional work, some switching from bulk optics to maybe fiber bundles or something like this. And we'd like to also lower the device of the cost. So because this is like a photonic industry meeting, I decided to add additional slide that will give you some hints about what kind of tools we are using in this optical research around the AI. So we have two paths. One is on the left. We develop novel system, or we focus on basic science, and then the price tag of the components is not so important for us. If it's expensive, yeah, we like to have it like, get it cheaper with some discounts, but we can live with this. And on the other hand, we have more like product-driven approach. And usually when you do some market analysis, you end up with this information that you should move toward low cost. And it was actually the market for this 9-spot approach that I showed you on previous slide. And then also some small footprint solution. So on both, we have light sources. For this 2-photon, we use pulse lasers, so nanoseconds to femtosecond regime. For OCT, we use swept lasers. And for standard OCT, let's say, we use lasers that tune the wavelength with more than 100 kilohertz repetition rates. Bandwidth depends on the spectral range. It can be around 100 nanometers, and ideally, output power should be around 20-30 milliwatts or more. For this full field OCT, so stock T approach that I show you already, we go to the slightly different approach. We use slow laser, so it's sweeping around 1 kilohertz. The bandwidth will be from 75 to 100 nanometers. Also depends on the central wavelength. It can be 800 or 1060. And in this case, we would like to have powerful. So probably if you can deliver something that is more than 50 milliwatts, we will be happy. And perfectly, it will be sweeping linear in wave numbers. On the right hand, so this more like product market stuff, we still can use the standard OCT lasers, but I grade them out, so maybe it's not so important approach. But if you want to go to low cost, the approach is to slightly lower the specs of the laser, so we can, let's say, reduce the repetition rate to a few kilohertz. We can shrink the bandwidth, and then still we'd like to have few milliwatts of optical power. And the current approach is with this, if you use VCSEL diodes with current tuning, so there is kind of internal heating process that will tune the wavelength. And then on detector sides, with these novel systems, or when we do basic approaches, we have digitizers that work in gigahertz range. In some cases, we require nonlinear sampling, so like K-clog. The example of this company that produce such digitizers is Al-Azhar. And these are pretty pricey. So usually it's second most expensive element after the light source. And we have ultrafast for this full field OCT. We use ultrafast cameras like Proton company. These are very expensive. They are not designed for science. And basically, I haven't seen solutions that are outside visible range. So for some cases, we like to have like infrared, like 1060 or around. Detectors on the right side, because we have this low spec laser, and if we look at those simple equation in OCT for resolution and maximum range that you can measure with OCT, you can kind of easily notice that for low spec laser, we can end up in a low spec digitizer. So we can use basically lower sampling frequency, and then you don't have to pay like 70K euro for the digitizer, but maybe a few hundred euro or dollars. So this is kind of space that we can move on. I think what is marked in the red, so this the slow laser with this pretty broadened bandwidth of tuning, it's really important because it's for this new generation of OCT. I think this is the future of this retina measurements. Maybe pharmacy will use it to study the drug developments and so on and so on. And actually, it was a big problem with those because these were produced by Russian company. I mean, not Russian, the company that used some Russian components. Part of this company is based in Ireland, but the key components were produced in Russia. So for a long time, there was no access to those sources. We had 2 or 3 of them, but if you want to develop new devices or something's get broken, you are done. So this is really interesting space for industry to catch up, because I think there is future, and also in this low-cost VCSEL tuning diodes for low-cost products. So I will stay with this nice photo of ICTER family. If it was kind of introduction, I went through those ideas very briefly. If you are interested, we can explore specific topics. So you can look at ICTER website, or you can email me, and we can maybe discuss things in details later on. Thank you.
Thank you very much, Carol. Really nice summary of all your work there at ICTER. So we have time for questions. We are a bit late, but we still have some time if anybody wants to ask a question. Regarding the work in the near infrared vision that you mentioned briefly by Kasia, what do you think will be the final application in the normal life, let's say?
Yeah, I mean, so for 2-photon, those kind of equivalent measurements for vision quality, let's say, from visual optics, it's really promising because it seems that the sensitivity thresholds are slightly different. The other thing is that for some patients, let's say with cataract, you cannot reach the retina with visible light. There are hopes that you can do it with infrared light, so with this 2-photon processes. But probably some potential with some displays with 2-photon approaches. Hard to say how well it can work. On this full field approach, so right now we are working at 800. There were sources at 1060, but there is lack of detectors. So those ultra fast cameras are usually used for manufacturing quality check, and they were never thought as science tools. So if someone develops ultra fast cameras with sensors that are sensitive for 1060, 1.3 micron would be interesting. And it's also they are not well designed for the amount of data we are collecting, basically, for the measurement. So usually you take the measurement and then you wait 2 hours to copy this from the camera to the computer.
Okay. And I would like also to talk with Laura from Modulite, because you presented this OCT solution for working with surgical tools. I don't know if Modulite you explored, that you presented your surgical laser, if you explore OCT as a technique to include in your surgical laser as a complement to evaluate the eye during the surgical process, or is something that is not in your mind, Laura?
That's a great question. So the laser that I presented, it's a PDT laser. So it's not, so to say, surgical or anything like that, but you do present a great point of maybe utilizing these surgical techniques for the eye in the future. So that's something that we can definitely discuss.
Yeah, so for imaging, we basically use I think they are class M1 lasers. So not the same laser that, let's say, people use for correction refractions. They are kind of strange in terms of perspective. So you have to tune the wavelength automatically with some repetition rate. And the instantaneous line width should be pretty narrow, so we'll have coherence properties along greater depths.
Yeah, I was just came to my mind while looking at the presentation from Carol. I don't know if we have any final question from anybody. If not, thank you again, Carol, for being here today. It was great to see your
Thank you.
presentation. And also thank you for putting on the table the needs for the future and what things should be perhaps developed so the manufacturers can think the way they can proceed from now on. Thank you again.
Thank you.
And yeah, we are reaching the end of the meeting. Sorry that we are a little bit late today, but I think it was really interesting and some interesting discussions as well. So thank you to all our speakers this afternoon. And thank you again to Modulite and Hamamatsu for supporting our meeting. It was a pleasure, and I hope to see you again in our next online meeting. Thank you, everybody, and good afternoon.
Thank you.
Thank you, Carol. Thank you very much.
Thank you very much.
Thank you.
Thank you, Laura.
Bye-bye.
Thank you. Bye.
Bye.
Bye.